Welcome to another episode of The Big Bang Theory. Well, not really Big Bang Theory, but we're going to do a lot of nerdy stuff in this chapter. So, first video, we're going to cover two sections together. It stumps me a little why the book would split it up between two sections like this, but they really work all together into one. And we're going to start focusing on trig, or trigonometric ratios. Now, trig sounds like a really fancy word that sounds really tough mathematically. But it's really not going to be that bad, and you're going to get a lot more exposure to this when you guys take pre-calc and calculus, okay? So, first, when we talk about trigonometric ratios, that's a mouthful. Like, I'm amazed I can even say trigonometric without screwing it up somehow. Anyway, let's think of the second term, ratio. Now, you've heard of the term ratio, but just in case some people are a little fuzzy on what a ratio is just a way of comparing two values to each other. Sometimes we can use the colon to represent a ratio, or we could use the word 2 to represent a ratio. But really a ratio is very similar to essentially a fraction. And that's what we're going to think of when we talk about ratios, or fractions. So I've got a ratio is similar to a fraction, and there are infinitely many fractions that represent any ratio. So for example, the ratio 1 to 2, okay, we can think of as 1/2. Which is the same thing as 2/4, which is the same thing as 3/6, which is the same thing as 4/8, which is the same thing as, and thanks Buzz Lightyear, to infinity and beyond, right? We really have infinitely many fractions we could come up with that are all essentially the same as 0.5 or 1/2 here, okay? So all these fractions really equal the same thing, this one specific value, okay? And that's going to be a key thing to understand why and how trigonometry, really works here. And we'll talk about more in depth here in a bit. Trigonometric ratios will allow us to solve missing sides and angles in right triangles. Okay, right triangles, just like previously Pythagorean theorem only worked in right triangles. We can only use trig in right triangles. Now, there are some special exceptions that we'll talk later this chapter about, but for the most part, right triangles. Now, here's the beauty of trig, is that it works in any right triangle. Whether we have little baby teeny tiny right triangles or huge ginormous triangles, right triangles that would be off the screen here. The size of the right triangle will not matter because we will be using ratios and fractions that all simplify to the same value in the end. Okay? So the size truly doesn't matter here of these triangles because we're going to be looking at two sides of each of these right triangles, and the two sides we're going to make into a fraction. And those fractions will be able to simplify to be one number, regardless of how big or small these triangles are. Now, the value, the ratio that we're going to be able to pull from, it depends on angles, okay? Now, we won't be able to use the right angle in right triangles. We have to use one of the two non-right angles. Does it matter which one we pick? It does not. Sometimes they'll give you one angle. For example, they might tell you how big this angle is down here, but they won't tell you how big this angle is up here. But using some basic math, if we know triangles have 180 degrees, and we know two of the angles, like the 90 and let's say this is 40, we know this top angle's got to be 50, right? Who are they really trying to fool? So we're going to be using the non-right angles, and it doesn't, again, matter which one we pick. Now, we're going to come up with, there's really 6 ratios of sides in a right triangle. And by ratio, again, we mean fraction. And we're going to use the sides to get our ratios. So, just real quick, you don't have to write this down, but, I've got 3 sides here, 1, 2, and 3. And so my ratios could come from taking any 2 out of those 3 sides and making them a fraction. So I could say taking the first side over the second side, or what about the second over the first? What about the first over the third, or the third over the first? And lastly, what about the second over the third and the third over the second sides? These are the only 6 ratios I could come up with using these 3 sides. All right, so those 6 ratios have special names, and that's what we're getting ready to talk about very soon. Now, in geometry, we're only going to cover half of the 6 ratios. The other 3, you're definitely going to use more so in pre-calc and calculus. All right? So theta, this little thing, it kind of looks like a 0 or an O, and it's got just, it's like got a belt, if you will. Okay? It's like we have an O, and we're like, hey, O, you look a little too big there. Why don't you wear a belt? We're like, okay, sweet. Slim down a little bit. I look like this guy. I look like a theta. Thetas are lowercase Greek letters that usually represent unknown angles. So, instead of calling an unknown angle x, we could call it theta, but really it represents the same thing as like we're calling it x. All right, so I pulled this from Wikipedia, just shows you, Wikipedia even knows that the Greek letter theta is used for angles in geometry. Let's get to our three ratios that we're going to have some names for. Now, on your calculator, you might have noticed an SIN, COS, and TAN button. And you might have always wondered, when are we ever going to use those three buttons? Hey, you're in luck. Today's the day. Now, the first ratio we're going to talk about, the SIN button on your calculator, it's technically spelled out sine. Okay, S-I-N-E is how you would spell this. This is just the abbreviation that can fit on your calculator. But the definition of sine, and this is a ratio, the definition of sine, and we're going to use our theta angle. Remember, I told you earlier, we're going to have to use one of the two non-right angles as kind of our starting point. Okay, so we're going to start with one of these two angles. So in this particular example, I'm saying, let's pick this angle down here. This is our starting off point for how we're going to be able to name our three sides. So the definition of sine is the numerator represents the opposite side of theta, and the denominator is the hypotenuse. So sine is always the opposite over hypotenuse. Now, for this specific triangle, we would say the sine of theta, so we're going to say this is the ratio we want to use, sine, and we're using theta as our jumping off point. Now let's apply the A, B, and the C to the actual definition here. So the opposite side of theta, well, that would be side B in this case. And the hypotenuse is, well, that's C. So we really don't need to know where theta is to know where the hypotenuse is, because it's always opposite the 90-degree angle. Okay, so again, sine is opposite over hypotenuse. The COS on your calculator, this is how you would really spell it out in full, is cosine. And cosine's definition of its ratio is we want the adjacent side of theta. And remember, adjacent just means kind of right next to, it's side by side, and we're going to divide it by the hypotenuse. Okay, so cosine again is the adjacent side divided by the hypotenuse. So mathy-wise, we would write it like this. We'd do COS for cosine. In our parentheses, we'd put in which angle we're using as our reference guide, and we're still going to use Mr. Theta down here. And so the adjacent side, well, here's the thing. There's two sides that are adjacent to theta. But C already has a special name, right? It's the hypotenuse, so that's going to be the denominator there. So that means the non-hypotenuse adjacent side, which in this case is, ooh, where are we at? Where are we at? Where are we at? There we go, A. Okay, so cosine again, adjacent over hypotenuse. TAN is for tangent. And it's going to be a little confusing later, towards the end of the school year. We're going to use the term tangent for something else. Okay, that kind of means something else in terms of circles. But the definition of tangent is we want the opposite side of theta divided by the adjacent side of theta. Tangent, again, is opposite over adjacent. Now, mathy-wise, we'd have tan of our theta angle. The opposite side of theta would be B, so our numerator would be B. And the adjacent side, remember, we already called C technically as our hypotenuse here, so the adjacent side would be A. So those are our main three ratios, sine, cosine, and tangent. And you might wonder, well, what about the other three that you said that we're not going to talk about in here? Well, the other three are just the reciprocals of the three that we're already talking about. So if we took tangent and flipped it, then this is technically called, if I can spell it here, cotangent. And the reciprocal of cosine is secant. And the reciprocal of sine is cosecant. So again, those three we're not really going to focus on. Now, the legend of Sohcahtoa. This is a nice, hopefully easy way to remember sine, cosine, and tangent and their definitions. So the S, the C, and the T, we're going to write vertical here. S is for sine, C is for cosine, T is for tangent. And I'm going to put a little equal sign after the S, the C, and the T. because we're going to make basically the equations, the formulas for sine, cosine, and tangent based off this. So the O, I'm going to use 3 letters here. Let me get a different color here. Sine's definition was opposite over hypotenuse. So I'm just going to do OPP, and then I'm going to put a little slash here to represent divided by, and then HYP for hypotenuse. Cosine, I'm going to call ADJ for adjacent divided by the hypotenuse. And tangent was opposite over adjacent. So this might be, like when you first get the quiz, you first get the test, you're like, man, I really have a tough time remembering the definitions of sine, cosine, tangent. You could write out got to get those H's in there, Toa, Sohcahtoa. Now, the reason why I have the legend of Sohcahtoa, there's a really lame story that goes behind it by saying there's an Indian named Sohcahtoa, and no, he's not really, his name was Sohcahtoa. Anyway, there's an Indian walking along, say, the riverbanks, and he stubs his toe really hard. He goes to the doctor. The doctor says, oh man, your toe looks really bad. What you need to do is go home and soak your toa in some water. Get it? Sohcahtoa, soak your toa. It's really lame, I know. You're all laughing, but it's all right. Now let's apply. So his first example's purely definition of what we're doing here. We're going to name the sine, cosine, and tangent of angles A and B. Okay, so we're going to work with both angles. So I'm going to go ahead and pre-write out sine of, then in parentheses, so let me do parentheses here. Come on, let me do parentheses. Come on, I know you want me, let me do it. Being a pain. So we'll say sine of A in parentheses. We'll have cosine of A. This is tough when you got to write with the mouse, since my board is being a little mean. And we'll say equals, equals, equals. So the definition of sine, okay, what was the definition of sine? Well, it was opposite over hypotenuse. So we're using angle A as our jumping off point. So what is the side opposite of angle A? Well, in this case, it would be W. And we wanted to divide that by the hypotenuse, which is R. So the sine of angle A would be W over R. And you might be thinking like, man, if this is the type of math we're going to be doing, this is really screwed up. This is purely an example to get you to understand the definitions and to apply the definitions. We will do some actual solving with sine, cosine, tangent by the end of the video. All right, cosine. Let's erase this stuff here. Cosine now. Come on, let me do it. There we go. Cosine of angle A. The definition was the adjacent side, and it's got to be Q because we already called R the hypotenuse. So the adjacent side is Q, hypotenuse is R. So we're done with cosine. We applied it. And last but not least, the tangent of angle A. Well, the tangent is the opposite, which was W, over the adjacent, which was Q. Now, what I want you guys to do now is I will let you do the sine, cosine, and tangent for angle B. So right over here, sine of B equals cosine of B equals tangent B equals. And I want you to write out those 3 ratios. So using angle B now, remember we got a different starting off point here, you'll notice that, maybe your opposite side isn't the same opposite side as it was before. Maybe the adjacent side quite isn't the same side as it was before. But the hypotenuse, there's only one hypotenuse in a right triangle, so it doesn't really change. But just keep in mind, your O and your A, they're going to flip around on you there. All right. Now, before we actually get into the solving bit of this, here's the thing. We're going to use our calculators to get values for us, sine, cosine, and tangent. Your calculator basically uses a lot of calculus to be able to get these values for us. So we're just going to go, hey, thanks calculus, but we'll take the numbers from the calculator. Now, if any of you have a graphing calculator, like the TI-83s, 84s, the big, $100 calculators, you're going to want to find the mode button, and you'll see degrees and radians is probably selected. You're going to want to slide it over to degrees, press enter so it saves it as degrees, and then exit out of there. If you have one of these calculators, like the newer TI-30Xs that like I would have in my classroom, you're going to need to do one thing here. You're going to need to go and find the mode button, wherever it may be, on the TI-30XS. It's right up here. And you're going to want to switch. It should already be on math print, but you want to go to classic. Okay, so switch that if you have one of these calculators. If you've got the normal calculators like I have in class, you won't have to worry about it. All right, so once we know which trig ratio that we are going to use and set it up, then we're going to solve it. Okay, so here's where we're actually going to get down into the oh man, what are we doing? I don't need you. Okay, there we go. We better? I think we're better. Again, this is where we're actually going to get into the solving part here. So we're going to look at one problem two different ways, and I'm just going to prove to you and show to you that it doesn't matter which angle that we pick. But again, we can't pick the 90. Okay, so if we're going to use the 40-degree angle, so we're going to use the 40 as our starting off point here. And I've got an unknown value, x, and I know this side down here is 6. Now, I can't use the Pythagorean theorem to get x because I would need to know what the length of this side is to use with the 6 to get the x. So here's where trig really comes in handy. So let's label our two sides here, okay? Eventually, you'll get to the point where you'll go, boom, I know which ratio this is. This is sine, cosine, or tangent, and you'll know it. But it's going to take a little while, get a little practice before you can fully recognize these. So I know x, it's opposite the 90, this is the hypotenuse. And the 6, this is the adjacent side. So was it sine, cosine, or tangent that dealt with adjacents and hypotenuses? And that would be cosine. Cosine worked with adjacents and hypotenuses. So let's write out how cosine would work out here. We'd have cosine, and we would use our angle, which we know in this case is 40. It's not just theta anymore. But cosine of 40, and that's equal to, and now we're going to apply the definition, which was the adjacent side, which is 6, over the hypotenuse, which is x. Now here's one thing I want you to do, just so you understand what cosine 40 is really going to do for us. In your calculator, type in cosine, type in 40 in the parenthesis, press enter, and it's going to give you a decimal, okay? And the decimal that I see is 0.766044443. So just understand that sine, cosine, and tangent of an actual angle is nothing more than just a decimal number, okay? This is our ratio that we're going to get, that singular value that all of our fractions will equal to in the end, all right? So we could, instead of write cosine 40, we could write in what its decimal is. But I want to leave it as just cosine of 40 right now. Because if you want to write out the decimal, you're probably going to want to round it. Which means when we finish solving this thing, we're not going to have as exact of an answer as we could if we had just left it as the cosine of 40 for now. All right, so now, what are we going to do now to solve this thing? We got cosine 40 equals 6 over x, keeping in mind that cosine of 40 is just some number. It was that crazy decimal. So how am I going to solve for x when x is in the denominator? Well, let's do this. What if we multiplied both sides by x so that the x is no longer in the denominator? All right, so it's gone. So we can say, all right, now we really just have the 6 over there. Ooh, whoa, that's crazy. We'll just leave it there. Now, if I want to get the x all by itself, it's being multiplied by the cosine of 40. Remember, the cosine of 40 is just a decimal number. So how are we going to undo a multiplication with the decimal number? We're going to divide that decimal number over to the other side. Now, that's gone, and here's what x is going to be. This is where you now get to grab the calculator and go, all right, what is 6 divided by cosine 40, end parenthesis. And I get my calculator that x would equal 7.832443736. This is where we're going to round. And I'm going to round it to, I don't know, 2 decimal places. So I'm going to go 7.83. I'm going to cut off there, chop off everything else. And that's how long the hypotenuse is in this right triangle. It's 7.83. Now, let's do this problem, the same problem. So we should get the same answer of 7.83. But what if we had picked the 50-degree angle instead of the 40? You know, will this setup look exactly like with the 40? The answer is no. So let's look with the 50. We're going to use the 50. Now, which ratio, sine, cosine, or tangent, works with the 50-degree angle? And will it be the same as when it was with the 40? Or are we going to use cosine again? I don't know. Let's see. So the 6, it's the opposite side. And the x, well, x is still the hypotenuse. Come on, let me write hypotenuse. You let me write it over here? No. Okay. Well, you let me write down there, but you won't let me write up here. Racist. Jeez. Back to the mouse. HYP. So which ratio, sine, cosine, or tangent, dealt with opposites and hypotenuses? Well, that was sine. So we're going to use sine to solve for x in this problem. And so let's set up the ratio here. So we're going to use sine with our 50-degree angle. So sine and then the 50-degree angle in parentheses. And that's going to equal, and now let's apply our definition of sine. It was opposite, which was the 6, over the hypotenuse, which is x. So this part stayed the same, right? Because when we did it earlier with the 40, it was 6 over x. But the difference is going to be the sine and the angle, or really the trig ratio with the angle. Now to solve this thing, we're just going to do the same thing we did before. Let's multiply both sides by x. Boom, gone. And then let's divide the sine of 50 over. Now the sine of 50 is, again, just a decimal. So we're just going to divide this decimal over. We don't care what the sine of 50 is as a decimal, because now we're going to throw it into our calculator. So 6 divided by the sine of 50. Hey, what do you know? I get the same exact answer I did before. So I want to change my equal sign to an approximate sign, and we got 7.83. So I got the same exact answer for the hypotenuse that I did when I used the 40-degree angle. So hopefully that's proof enough for you that it doesn't matter which non-right angle you select, you will get the same final answer. You may just have a different ratio to use. All right, let's do number 2 together. All right. Now, this problem, we're going to use the 76-degree angle. We could figure out what this other angle is down here, but we're just going to go ahead and use the 76. So we need to figure out which ratio are we going to use with the 76-degree angle so that we can apply its definition to be able to write, will it be x over 24 or 24 over x? So let's label our two sides here. Well, the 24 is the hypotenuse because it's opposite the 90-degree angle, and the x is the adjacent side. So was that sine, cosine, or tangent that dealt with adjacents and hypotenuses? Oh, it was cosine. Okay, so cosine with the 76 is equal to the adjacent side over the hypotenuse. Now, we want to solve for x. Here's x. In this case, we don't have to multiply x over because x is already in the numerator. All we got to do now is multiply the 24 over to the other side, and this is what we want to throw into our calculator now. So 24 times cosine 76 in the parenthesis, I get approximately, I'm going to go 2 decimal places, 5.81. It's 5.06, but the 6 is going to bump my 0 up to a 1. And there's the approximate value of x. And that's it. Example 3. Let's do this one. So the 34, we know we're going to use 34, but what ratio are we going to use with 34? Sine, cosine, or tangent? So let's label our pieces here. The 5, it's the opposite side of the 34-degree angle, and the y, is it the adjacent or the hypotenuse? Well, opposite the 90, this would be the hypotenuse. So that means y is the adjacent. So what are we going to use with opposites and adjacents? Well, that's tangent. Okay, so we're going to finally use tangent with our 34-degree angle, and it's equal to the opposite side, which was 5, over the adjacent side, which is y. So now to solve this thing, we want to get y, but y is in the denominator. So here's where we're going to multiply the y over, and then we're going to divide the tangent 34 over. And again, the tangent 34 is just some decimal number, but we don't care what it is specifically because now we're going to throw it into our calculator. So 5 divided by tangent 34 in parentheses is approximately 7.41. And we're done. Now, the last 2 problems. The last 2. Boom. We're going to switch that up here. I want you guys to try these out. Now, example 4, there's 2 sides you're going to have to figure out, x and y, which means that if there's 2 sides, you're going to have to do 2 problems. Okay? So you're going to have to set up 2 different trig ratios. Now, I gave you options here. Do you want to use the 75 or the 15? It doesn't matter which one you pick. Just make sure that if you pick, let's say, the 15, that you label the sides right here. Which one's the opposite? Which one's the adjacent? Which one's the hypotenuse? Now, hopefully you guys recognize here that if I use the 15 and this is the opposite, adjacent, and hypotenuse, using tangent probably isn't a good option here. And you might go, why not? Why can't we use tangent? It's opposite over adjacent. Oh, there's two variables if I try to use tangent. So yeah, probably not a great idea. So I want you guys to try example 4, and I want you guys to try out example 5. Now 5 looks tough. Oh, it's a word problem. It's crazy. But use the information here. You might, really the only quote-unquote tough part, I would think, would be how long is this piece, knowing that this whole piece down here is 82, and hopefully from our last chapter on pyramids, you can easily figure out what that bottom piece is. And they want to know how tall the pyramid is. Well, that would be our actual height. And I want you, in this case, round your answer to the nearest meter. So don't worry about to 2 decimal places, round it to the nearest whole number. Now, we are going to be doing this chapter for a while. This is like one of those 3 to 4 week long chapters. So don't freak out on me if you're like, oh my gosh, this was like crazy voodoo math. I have no idea what in the world he was talking about. We will definitely practice a lot with this. So don't worry. And that's all for this first video.